All right, so right now we are working on 1991, question 1, and we see that it is the monkey problem. And we have this 5 kilogram monkey that hangs initially at rest from 2 vines, and each of the vines has a length of 10 meters. And so they basically just gave us extraneous information by saying 10 meters, because that really doesn't matter at all. The length does not matter in the tension. The only things that matter in the tension are going to be that mg of the monkey and our angles. So on the figure below, draw and label all the forces acting on the monkey. Do not resolve the forces into components, but do indicate their direction. So resolving the forces into components means they don't want to see any angles. They don't want to see any kind of other lines except for the 3 forces that are acting on the monkey. And so we see that we have got this tension B, so T of B. We've got this T of A, and then we've got this mg. And what this part B wants is find the tension of vine B while the monkey is at rest. And so because this problem does require a lot of space, I'm actually not going to do it on this piece of paper. I'm going to do it on this piece of notebook paper. And so we want to find this tension B. And so what we're going to do for part B is we're just going to redraw our free body diagram. So let's redraw it. We've got our T of B, we've got our T of A, and our mg. And what we're looking for is this T of B, but we also don't know what T of A is. So we have 2 unknowns, therefore we're going to have to make 2 different equations. So the first equation that we need to make is the sum of the forces in the y direction, which we know are going to equal 0 because this monkey is not moving or accelerating or anything like that. And so looking in the y direction, we need to see, so first of all, we need to look at where our angles are. And we see that they've given us this angle right here and this angle right here. So this is theta B and this is theta A. And so we see that due to geometry and all of that other wonderful stuff, that this angle right here equals this angle right here, and then this angle over here is going to equal this angle right there. So we see that we have got these 2 angles, and so what we need to do is, let me redraw this because now it looks all kinds of crazy. So we've got our T of B and our T of A, and so we see that these tensions are not in the x or in the y direction exactly, and so we're going to have to break them up into, so this is T of B in the y, and this is T of A in the y. And you see that you've got 2 different strings, so you have 2 different tensions. And so we see that they're pointing in the y direction, the same direction as this mg. And so we get the sum of the forces in the y direction equals 0, which equal our T A in the y direction, plus our T B in the y direction because they're pointing in the same direction, minus our mg because it's going down. And so we see that that is our kind of basic equation for this. And so what we need to do is we need to draw 2 separate triangles because we see that we have one triangle right here. We have the other triangle over here. So let's talk about our T of A first. So let's draw that not that equation, but that formula. And we have got this T of A and this T of A in the y. And this will be our T of A in the x. And so right now we're looking for this line right here. We know, well, we don't know this, but we need to express this TA in the y in terms of T of A. And so how we're going to do that, we're going to see this is our angle theta A. And so we see that this line has a opposite relationship, so it's going to be sine theta equals TA of y all over T of A, and then multiply your T of A on both sides. And we end up with TA in the y equals T of A sine theta. And so that's going to be our y direction, our tension A, and the y direction is TA sine. All right, so now let's look at B. So for B, we've got this other triangle. So this is our T of B. This is our T of B in the y direction, and that's going to be our T B in the x. And so this is going to be our theta b, what they give us, which is our 60 degrees. And so we said that TBY also has an opposite relationship. So we're going to say first we're going to say sine theta b. This is sine theta a, by the way. So sine theta b is going to equal our TB and the y, our TB, times our TB on both sides, and we end up with TBY equaling TB sine theta b. And now we have these two, so we can plug it in for this up here, because we have to have this expressed in tension B and tension A. So we get 0 equals our TA sine theta A plus our TB sine theta B minus our mg. So this is one equation. So we've looked at this TB and the y. Now let's look at in the T of A and the y. Now we need to look at it in terms of the x. So let me redraw this free body diagram and we'll look and see what it looks like. So this is our TB, this is our TA, this is our mg. And we see that this TB in the x direction is pointing to the right. So this TB is pointing to the right. And then, oh crap. And then this T of A is pointing to the left. So when we talk about these terms, they're pointing in opposite directions. So we see that the sum of the forces in the x direction equals 0 because it's not accelerating. And we get T of A in the x direction minus T of B in the x. But we can't keep it in terms of that. We have to put it in terms of T of A and T of B. So we need to look at, again, these triangles. So looking at these triangles right here, we see that both of these have adjacent relationships with our angles. So T of A in the x has an adjacent relationship with this angle theta right there. So it's going to be cosine theta A is going to equal the T of A in the x all over T of A. And so multiply your T of A by both sides. So we get T of A in the x equals T of A cosine theta A. Now looking at this one, we see that our TB in the x is going to be adjacent to the angle. So we get cosine theta B is going to equal TB in the x direction all over TB. Multiply our TB by both sides, and we end up with TB in the T of B in the x direction equals TB cosine theta B. Now we can put this in that initial equation up here, and so we get 0 equals T of A cosine theta minus T of B cosine theta. Now we've got two equations that we are going to be working with right here.